Hello, everyone. My name is Priyesh Chakraborty, and I'm a second-year graduate student at Harvard University. Thank you for being at my talk today. I will be speaking about the CMB cross LSS Skew-Spectrum, which was work done alongside another graduate student, Shufan Chen, and Professor Koyad Walken. But you can read more about our work at this archive link. So this is a broad outline of my talk. First, I will be providing some background on CMB lensing, cross-correlations, and non-Gaussianities for those who are unfamiliar. Then I'll discuss the Skew-Spectra, the theoretical motivation, and an algorithm to estimate it from the data. Then I will present a Fisher analysis in order to gauge the information content of the Skew-Spectra relative to the bispectrum. Finally, I will present an analysis of simulations using these Skew-Spectra as a first step before applying them to the data. So today in cosmology, the state-of-the-art constraints on cosmological parameters are obtained using the CMB temperature and polarization data. However, there are still potential issues. There's the H0 tension, E tension, and a wealth of new physics that remains to be constrained. Now, large-scale structure data offers a way to probe these questions. Since large-scale structure surveys can in principle access an order of magnitude more modes, there's an avenue to resolve these current tensions and constrain new physics. However, in contrast to the CMB, large-scale structure data is highly non-Gaussian. So it contains a lot of information in higher-order correlation functions, such as the bispectrum, which has only recently been started to be analyzed for example, for the BOSS survey on the right. So let's get started with our data sets. The first is CMB weak lensing. Now, the CMB photons, after being emitted from the surface of large scattering, are gravitationally lensed by the matter along the line of sight, and this gravitational lensing can be captured by this angular field D in this equation, which results in a statistical anisotropy. However, in practice, we only care about the divergence of this field, which we call the convergence or the CMB weak lensing convergence. Now, the weak lensing convergence is simply a line of sight integral of the matter fluctuations modulated by a window function, which peaks roughly around redshift of 1 to 3, which you can see on the shaded region. And since it traces matter fluctuations, it's highly correlated with galaxies, especially in the shaded region on the right. The second part of our data set are galaxy maps, which are 3D maps of galaxies which contain both angular and redshift information. So in order to cross-correlate it with lensing convergence, we need to project these along the line of sight. And this projection is performed with the galaxy window function, which is simply the redshift the number density along the line of sight. Now, with the help of these two maps, we can construct power spectra, bispectra, and a number of polyspectra. But in this work, we'll be focusing on the three-point function of the bispectrum. Now, the three-point function of density modes can be broken down into a geometric piece given by this factor G, and the angular bispectrum, which is highlighted in red. And this contains all the non-trivial physics. So in theory, these angular bispectra can just be obtained by projecting the Fourier space bispectra along the line of sight. And these Fourier space bispectra can just be obtained using either perturbation theory or in body simulations. So in perturbation theory, an angular bispectrum can simply be written as a factorized form in L, modulo an integral along the line of sight, where these factors, these ILs, are in principle complicated integrals of the power spectrum along with some spherical Bessel functions. However, these can be computed efficiently and reliably using either the Limbo approximation or the F15 log algorithm, which we can read more about in this work below. So what sorts of non-Gaussianities are we dealing with? So in this work, we'll be dealing only with gravitational sources of non-Gaussianities. So What that means is the initial linear density modes, which are Gaussian, due to gravitational evolution, develop into non-linear density modes, which are highly non-Gaussian, which you can see in this illustration from simulation below. Now, this evolution can be captured by the AFT of large-scale structure and or another perturbation theory scheme. And under the AFT of large-scale structure, for example, the galaxy bispectrum can be written as a series of terms organized in Legendre polynomials with some prefactors which depend on the bias coefficients. So this is the galaxy bispectrum at tree level. Now, the important point is that it can be organized by Legendre polynomials, which I will ask you to keep in mind. Another source of non-Gaussianities for us are post-Born corrections. So this line of sight integral expression that I showed for the Lensing convergence is strictly only true under the Born approximation. However, it receives corrections due to lens-lens couplings along the line of sight to generate quadratic terms in the Newton potential, which in turn generate tree-level bispectra. Now, how do we actually measure these bispectra? So that can simply be done by considering averages along all triangles in Fourier space. However, this is a very expensive operation. Naively, it requires n³ steps and at best requires n squared log n operations. But that's still quite inefficient. We ask, can we compress this statistic efficiently? This is where the Skew-Spectra come in. Now, if our goal is to optimally capture the amplitude of the overall amplitude of the bispectrum, such an optimal estimator can be written in this way: some cubic estimator convolved with the theoretical template for the bispectrum. Now, we can ask, can this estimator be expressed as sum over a 2-point statistic? And this is exactly the Skew-Spectrum. It's simply the cross power spectrum between a quadratic field D and a single density mode, where this quadratic field D is just a quadratic combination of two density modes convolved along with the theoretical bispectrum. For multiple fields, this can be generalized quite straightforwardly, where all we need to change is we need to be careful about the bispectrum, the theoretical bispectrum that we're convolving with. Now, at this stage, I will note that estimating this quadratic field seems quite expensive. It requires n³ operations as before. However, I will outline how to simplify this shortly. But first, we want to ask, can we do better than this? Now, recall that the galaxy bispectrum in redshift space could be organized as by Legendre polynomials in this way. Now, the same is true for the galaxy bispectrum in harmonic space. It can be written as a sum of shapes, where each shape is determined by a line of sight integral of a single Legendre polynomial, with the combination of biases that appear as prefactors are maintained. Now, we can construct quadratic fields using these Legendre polynomial shapes instead, with the idea being that the Skew-Spectrum computed using this quadratic field will be sensitive mostly to the combination of biases appearing as its prefactor in the expression for the full angular bispectrum. Now, these are just some example Skew-Spectra, which are made for LSS specifications. On the top left, you can see the full Skew-Spectrum, as in the Skew-Spectrum obtained by convolving with the full theoretical bispectrum. And the rest of the three are the decomposed spectra, where each using each Legendre polynomial kernel. And now we want to ask, what the covariance matrix looks like. And you can see that the covariance matrix is highly off diagonal. So this is made using DESI ELG specifications, and this is typically the case that the covariance matrix is highly off diagonal. So in practice, we need to use the full covariance matrix to conduct a likelihood analysis. So now we want to ask the benefits of using these decomposed skew spectra, by which I mean using each individual Legendre polynomial kernel to generate skew spectra instead. So to do this, we want to do a Fisher forecast for the bias and A short parameters for a single DESI ELG redshift bin. Now this parameter A short is simply a free parameter that we keep in our analysis, which contains modulates the overall amplitude of the short noise contribution of both the power and the bias spectrum. So let's look at our results. You can see that so we're obtaining constraints for the decomposed spectra, the undecomposed spectra, and also bispectrum. And the decomposed spectra agrees almost exactly with the bispectrum, whereas the undecomposed one not only has worse errors, but also has tilted degeneracy lines. So clearly, the decomposed spectra contain more information. We can see why this is the case by looking at this equation. You can see it's clear that the decomposed spectra can be linearly combined in order to obtain the full skew spectrum. However, this is not invertible. This shows that the decomposed spectra contain more information. So now that we know that it's useful to compute the skew spectra, we can have a look at how to estimate these spectra in practice. Now, the quadratic field required a non-trivial convolution to be performed with this Legendre polynomial shape. However, if you recall, the full bispectrum can be written as a factorized form, and the same is true for these Legendre polynomial shapes, modulo an overall integral line of sight. Now we can combine each of these factors with a single density mode, and combine and write this combined field as some larger field, which I call capital delta. And now the convolution has been made trivial. Now we can simply perform a product in position space of these larger fields delta and perform an FFT modulo this overall line of sight integral. So there you have it. So this is the same steps that I showed above, written in algorithmic fashion, and you can see that estimating the quadratic field and therefore the skew spectrum itself from the data has been reduced to a sequence of FFTs. So therefore, this requires only n log n time, as fast as a power spectrum. So now we want to get a more complete sense of the information content of the skew spectra, which we study using DESI ELG cross-Planck lensing specifications. These are some details of our Fisher analysis. We use Gaussian likelihood. However, for our parameters, we choose to vary even the non-amplitude cosmological parameters in order to get a more complete sense of the information content. Finally, although we fix our K max to b.1, so that we remain in the tree level regime, we still incorporate non-linearities using a fitted SPT pun, which accounts for non-linearities. So this is just a minor detail. So here are our results. This bar chart, I'm showing the relative difference between the skew spectrum and the bispectrum for the marginalized errors on each parameter. So as you can see, the cosmological parameters do very well. They the relative difference is consistently under 17%, and for the biases, it's consistently under 12%. The only exception to this is A short, which showed a relative difference of 50%. So motivated by this, we want to conduct an analysis of simulation data, for which we're using the massive news halo catalog, and we would like to estimate the bias and A short parameters from them. We also use lensing maps, which we generate from the simulation data using the publicly available code lens tools. So some details about our simulated maps. These are angular maps of 3.5 square degrees, for which we use the flat sky approximation to conduct our analysis. So we impose a sharp cutoff at an angular scale, which corresponds to a K of 0.5, so that all of our theoretical models remain in the region of validity. And our minimum halo mass is order 10 to the 12 solar masses. So these are our results of the MCMC analysis. Here I'm showing the middle 68% errors for the biases and a 68% lower bound for A short. Now we conduct a separate analysis for using just the halo maps, and a separate one using halo and CMB lensing. And although you can see that the halo maps are enough to constrain all of these parameters, CMB lensing tightens the constraints on each parameter. In particular, I'd like to highlight that we seem to be able to measure the linear bias to percent level accuracy. So this is our posterior. As before, you can see that the halo maps are enough to constrain each parameter on its own. However, adding CMB lensing tightens the contours on each parameter. And this is the estimated halo skew spectrum. So the dashed line is the average of the halo skew spectra estimated from the simulations, and the dots are simply the theoretical halo skew spectra using the best fit bias and A short parameters, and the error bars are reduced using the analytical covariance matrix. As you can see, there's reasonable agreement within error bars. Okay, so just to summarize all I've said to you, we managed to compress the information of the bispectrum into a skew spectrum for the CMB cross LSS case. And we found that it was also, even though it was designed to be optimal for amplitude parameters, we found that it was also able to capture non-amplitude parameters up to 17% of relative error with the bispectrum. We also outlined an algorithm to efficiently compute it from the data, which is as fast as a power spectrum, requiring only n log n steps. We also tested our model on the massive mu simulations, and we were able to constrain the linear bias to percent level accuracy. So for our future work, we're conducting an analysis of Gauss data using Skew-Spectra in redshift space. So I would ask that you stay tuned for those results. Thank you for your attention.